change this to gallery view. Which, can I force it to show? No, I'm hoping that this is going to show me in the recording itself because I'm the one who's talking. But that's not what's showing up in my screen. No, come on, speaker view. I don't know why it's showing me that. What, Easton? Sorry, I'm just trying to get this to see if it shows me. There we go. Okay. Because the last time I did the lab, it was this tiny little thing, and I didn't want to have to redo things twice because that's pointless. But otherwise, if we... No, you cannot have a snack. Share screen, there we go. I know he does, but he's gonna have to wait. Okay, so page 5 of the notes should be, come on, this page. And I'll move probably this over to this side. So we've got some different categories of rocks here. We have a definition for a rock. And I kind of mentioned this definition a little bit with the mineral notes a while ago. We have a rock is made up of minerals. So if you smush a bunch of different kinds of minerals together, you can pretty much call it a rock. So a big part of it too is that it's naturally formed. That was one of the big criteria for minerals as well, is if we make it in a factory or a laboratory, things like that, technically you can't call it a rock, but I'm sure you'll get away if you do call it a rock. Okay. So they're solid, meaning magma and lava doesn't count as a rock because it's liquidy, and it's a mixture of minerals. So I think at one point in time, I had talked or given the example of like a cookie representing rocks and minerals. So a cookie is made up of different parts. You've got your flour, your butter, your sugars, and baking soda that kind of go into the dough. And then you've got other parts in there that are nuts if you're crazy and like disgusting cookies, or chocolate chips, or some of the yummy delicious things. Each of those individual parts that go into a cookie would be like the minerals. And the whole thing, the cookie itself, would be the rock. So just kind of wanted to really make sure that we know the difference between a mineral and a rock. And a really good one, if you've got granite, whether it's, I don't know, countertop or anything like that. I've got granite right here, which it's really glaring a lot, but there's lighter colors. This has actually got pink in it, which is the mineral feldspar. And then there's these darker ones, which are probably like gabbro or basalt or something like that. There's different minerals that make up this granite. And granite is a really good one to look at for this explanation because you can, the crystals are really big, the minerals are really big. You can actually see the individual minerals, go, hey, I can point to this mineral, I can point to that one. You can see the differences. Some of them I'm going to show you, you'd have to see them through a microscope of some sort to actually see the individual mineral grains. So it can be a little tricky, but otherwise, I'm going to show you the 3 types of rocks here today. We're going to talk about them. First one is a kind of weird word called igneous. Igneous rocks formed from cooling magma. So these are the lava rocks, the volcanic rocks. The two big ways that they form, and it's actually the two big categories of igneous rocks, depends on whether they form inside the earth from magma or they form from lava on the surface. What's up? Did he? I'm sorry. Are you better? Do you want to say hi to the class since you came down here and interrupted? Or are you good? She doesn't want to say hi. Okay. The other big group here is sedimentary rocks. So it's got the word sediment in it. These are the ones that form from tiny pieces of other rocks, which is what a sediment is. So this could be sand sediments. It could be clay that forms them. It could be pebbles or boulders or any chunk of rock that gets smushed to other chunks of rock forms a sedimentary rock. Okay. And then the last category here is called metamorphic. I suppose I should pull up my chat so I can see if there's any random people that are trying to join. Yep. Okay, so metamorphic is the third type of rock here and the last type, big category. Metamorphic should sound like metamorphosis, like a butterfly or tadpole metamorphosizing into a frog, that kind of thing. Because these are the rocks that go through some type of change. So they used to be one type of rock, but then they got covered through plate tectonic activity where the plates like smush into each other and it causes rocks to get buried and move lower. And when they move lower, they increase their temperature. And obviously if they're under a bunch of rocks that are above them, it's going to be pretty high pressure because they're getting squished by a mile of mountain or something like that. So it's the heat and pressure that changes these rocks slightly. It does not melt them completely, because then that would form magma and lava, and then when it cools, you would have an igneous rock again, not a metamorphic. So it's just enough heat and pressure to change them without melting them is the big key there. Okay. So that brings us to a little diagram. Joining us, it looks like. So we call this the rock cycle, and we've got a couple worksheets that we'll do next week that kind of go along with this, but I guess I should just get rid of this at this point. Get this out of my way. Okay, so I guess we'll do the top part here. You see we've got some different boxes and arrows that we're going to be connecting. We're going to be labeling some different things. So I'll give you a moment to copy these down. You notice that the types of rocks are in circles. So I've got sedimentary rocks up in the top right circle. I've got metamorphic in the bottom right circle and igneous in the bottom left circle. And then I've got some things in boxes in between, which is kind of their halfway in between steps, what they form in between some of these different types of rocks. So I've got sediments in the top left box, and I'm pretty sure I've got magma or lava. Either one would work there. Magma and lava in the bottom box. Okay. And then the arrows. The ones in the middle aren't labeled, but you technically could. And I'll talk about that later here. The ones around the outside are labeled. And the arrows represent processes or things that can happen to rocks throughout their lifetime. So if I'm going to go from a sedimentary rock to a metamorphic rock, I have to experience heat and pressure. What this means here, the arrows. If I'm going to go from an igneous rock to a sediment, I have to go through weathering and erosion. which those two are worth describing and maybe defining a little bit more than that, because we haven't done a weathering or an erosion unit at this point, and I think I had in my 8th grade earth science class before this. So weathering and erosion are pretty similar to each other. You might have used them in the same way, like you might have used them interchangeably. When you said weathering, you might have actually meant erosion, or vice versa. But there is a slight difference here. So weathering is simply just breaking up rocks into small pieces. Right? It's kind of over the arrows, but good enough, I think. Okay, so if I took a hammer and I smashed a rock, technically I would be weathering it. How it happens in the real world is you could have a glacier that's literally scraping rocks into small pieces. You could have rain that hits a rock and slowly breaks it down into small pieces just through friction, essentially. You could have a big one, and you might notice this with our wonderful pothole-filled roads around here. In the winter, when it freezes and thaws, the ice expands and breaks up asphalt, or it breaks up rocks that have cracks in them into smaller pieces that way too. So that's all that weathering means. Erosion is moving sediments from place to place. So weathering is the breaking it up. If it's like in my driveway, because I have a gravel driveway and it's on a hill, sort of, when it rains, I get like this river that forms on my driveway, and it washes away some of the smaller sediments from my gravel driveway and fills in another area. So that moving of sediments is erosion. Okay. So that's that arrow there. So whenever you weather or erode a rock, you're going to form sediments or move the sediments. And then some of the bottom arrows here that we can't see. So if I take a metamorphic rock and I go past my heat limit before it melts, so I melt it, it's going to form magma. So it just gets super hot and it's going to form magma. If my magma cools, it's going to form an igneous rock. Okay. So what we've described so far is the outside of our rock cycle. And the way it's drawn, like if I take away these arrows in the middle and make them go away briefly, they're almost away. What it looks like is if you are a rock, you have a predetermined life cycle. You're going to start as magma, you cool off, you turn into an igneous rock. Then that igneous rock is going to break down into small pieces, it's going to form sediments. Then they're going to get cemented or glued together or squished, compacted together to form sedimentary. Then that sedimentary rock is going to go through heat and pressure, and it's going to form a metamorphic, and then it's going to melt, and it's going to start the process over. So it's the way the outside of the circle is, and what I've described so far, makes it seem like rocks only have one path that they can follow. But what we can really have happen here is if a sedimentary rock has rain hitting it again, like it probably does if it's on the surface of the earth, or if it's going through freezing and thawing, it can break up into small pieces again. And it can go through, if it goes from sedimentary to sediment, the process that I could put there, which I don't have the arrow on, but I could write it there if I wanted to, is if I'm forming a sediment, I must be going through weathering and erosion. So I can draw an arrow any way I want to on this rock cycle, and I'll know what's going on. So let's follow this one here. Sedimentary is going down towards magma. So if I was going to label that arrow, I would probably be labeling it the same way I have the arrow going here. If it's going to turn into magma, it's going to be melting. I can have an igneous rock remelt and form magma again without it having turned into any of the other two types of rocks. I can have a sedimentary rock. Whoops. Oops, metamorphic, I guess. Metamorphic gets a bunch of rocks, or not rocks, rain and freezing and glaciers and stuff hitting it. It's gonna form sediments. So we can connect these any way that we want to. So an igneous rock could become a metamorphic rock without having broken down or turning into sediments at all. It just has to go through heat pressure. So, okay. Because I need you to leave me alone. Go grab a cupcake, go eat it outside. You like muffins? Well, these are cupcakes. They're better. Can you help Elena get one, please? Okay. So that's the main thing I wanted to go over today is this whole rock cycle here. We're going to have a quiz at some point on the rock cycle here, but I think we'll wait until we do another note session on some more specific details on each one of these three types of rocks. What I want to do at this point is I'm going to have to just double check that I get this muted and showing correctly, because I'm going to use my phone at this point. It's really weird to use a computer to show rocks and whatnot. But before we jump away from the notes, does anyone have any questions, whether you unmute yourself or do the chat? I really could care less.
I have a question.
Sure.
You said that erosion is through movement. So what makes a move?
Okay. So a couple things can make it move. There is the one that I described, which is water, whether it's a river, a big rain. So that water is going to flow downhill. When it flows downhill, depending on how fast it moves, it's going to take different size particles with it. If it's moving slow, it's going to take the smaller ones with it, like clay, which are microscopic particles of rock. If it gets a little bit faster, it'll move the sand, which is a little bit bigger particles. If it gets super fast, like a tsunami or a sudden flash flood, you might move bigger chunks like boulders or things like that. Another big one that moves it around here is wind. So like on a windy day, you might have dust that blows off of a gravel road or a field that just got plowed or things like that. And possibly the other biggest one would be glaciation or glaciers.
So the weathering is what breaks it up, but the erosion is moving it.
Yes, so erosion just has to do with moving it. All the
Okay.
weathering is smashing it up into small pieces.
Okay.
Okay, so I'm gonna go grab my phone, which I kept in the other room, just to prevent echoes, even though I think I had it figured out, but I'll be right back. Okay, let me get this all figured out here. Is it echoing?
No.
Okay. Why can I not hear anything though? Guess I don't really need to hear. Okay, let me stop the share because I think that's gonna make it always go to that. I need to mute. Start video. And let's see if it follows this. Go. Nope, it'll do it. Okay. Assuming you can see this at home, my phone.
Yes.
So let's take a look at some of these rocks. I have quite a few out here right now, and this whole line right here is actually igneous rocks. So these are all types of volcanic rock. And I kind of wanted to point out some of them that we heard about with the volcanoes. See this one, it says it's basalt. This was our basaltic lava that we talked about with the volcanoes. It had the least amount of silica in it, which gives it a darker color. You can also see in this basalt those little tiny holes or craters. This gives us a hint as to where this magma or lava cooled. Since it's got these holes in it, this is actually gas bubbles. And this means that this particular rock cooled very quickly and on the surface. So this formed from lava that had gas bubbles in it. Where if we take the same magma, but we cool it slowly, you're going to form this other one here, which is Gabbro. And it's the same color. It's made up of basaltic magma in this case. But if I move it around, you should be able to see a few sparkles every once in a while. So those are actually crystals. I don't know if it'll focus when I get this close. Kind of. These are larger crystals where if you look at the basalts, you see air bubbles, but you don't see sparkly crystals that are big enough to see with the naked eye at least. So what this tells us is the Gabbro, even though it's made up of the same magma, the same type of lava, basaltic lava, cooled very slowly on the inside of the earth. It didn't erupt out to the surface and cool quickly like the basalt did over here. It did it slower, and we know that because it's got a bunch of big crystals in it that you can see, and no air bubbles. Okay. Some of the other rocks here that we have andesite, which was the medium amount of silica from our lab. It's getting a little lighter. If I bring it over into the light a bit, you can see little tiny like black specks in it. Those are different mineral crystals, so this lets us know it's big enough to see a crystal on it, which means it formed inside the earth, I believe. And then we get to rhyolite, which has the most amount of silica from our volcano lab last week. And silica is white, so we've noticed the three I've just pointed out started out with a dark color, and as you put more silica into it, it got lighter. And this was the lava that was the thickest or the most viscous as well, and it created the most explosive eruptions, if you remember that. Okay. Some other ones. May have heard of volcanic glass or obsidian. So very shiny, it breaks just like glass would, and this is the kind of material that early cavemen, if you will, early man used, or even Native Americans when they were using bow and arrows or spears, they chipped this into very sharp pointy tools that they could use, whether it was an arrowhead, a spear, a knife, anything like that. And this is glass, and the crystals are so small that you can't see them without a microscope. When you do look at this with a microscope, it looks like clear glass with little flecks of black in it, actually. So it cools super quickly. This actually forms when magma comes out of the surface and touches water. Water cools it down really quickly. And then I showed us the granite. The granite itself, though, has those really big crystals. So this lets me know that I actually cooled very slowly inside the earth. So granite would be like the magma chamber of a volcano cooling down over a long time. It's underneath the surface. And then the last one I wanted to show, I think these are actually the same rocks here. They're called pumice, but I had a really big one that I found at school, and you'll notice it kind of looks all cratery. And I have my tub of water over here, and if I put this in there, what we will notice is the rock doesn't go down to the bottom. Volcanic rocks, if they are formed from kind of the lava that explodes out of the volcano, tend to have a lot of air bubbles in them. So that actually makes them not very dense, and you can actually float the rock. Like even if I push it down to the bottom, it'll pop back up to the top. So that's our pumice, is the fancy name for the lighter colored lava rocks. And those are some of the best examples there of an igneous rock. I wanted to show us some sedimentary rocks here. I was going to try to, this one is a sandstone that I actually found in my dirt as I've been trying to make retention walls. It looks like it has holes in it too, but that's just the gaps in the sand. But the big thing here, like if you see me, it's a rock, but I can actually scrape off. I'm actually weathering this rock right now just with my thumb. So I'm breaking it into this sand component. So that's sandstone. I'm gonna let the dog go quick. Go. Okay. So that's sandstone. That's what happens if you take a bunch of sand and cement it or glue it together, compact it together. We also have limestone, which there's a ton of limestone around here. Like if you go to any of the forest preserves where there's rivers and you see like cliffs, it's probably a limestone cliff. So limestone is all of the wonderful dead critters that have shells that live in water. They get compacted and cemented together. So this is like a lot of snails and clams and some algae like foraminifera, if you remember that from 7th grade with the Mesozoic and the dinosaurs dying and stuff. They have calcium carbonate shells, even though they're microscopic, and they form limestone. Then we have chalk, which is actually a sedimentary rock. It's similar to the limestone. It's just a little bit softer, so you can actually use it to draw and whatnot. And some of the things that's good for comparison here, we've got Metamorphic Rocks last. This one's marble, the one that I just grabbed. And if I take it back and I compare it to either the chalk or the limestone, they're all made up of calcium carbonate for the most part, which is calcium with carbon and oxygen. And if you take the limestone or the chalk and you bury it and it gets warmer and it gets a lot of pressure on it, it actually turns into marble, which they use to make statues with. It's a lot harder. And the other thing that's a really good clue that you've got a metamorphic rock is, can I get it to show up? You can kind of see some sparkles every once in a while. It makes nice little crystals in rocks that didn't have crystals before. That's a very big clue that you have a metamorphic rock, as you see shininess to them that isn't a randomly formed crystal. Like granite has got shininess too, but it's got very chaotic, sporadic crystals, not uniform crystals like a metamorphic rock. The other kind here that's a really good one that actually shows you both kinds, and I've already got it out, is the two things you look for a metamorphic rock, like gneiss or gneiss, I think they pronounce it, this Gneiss, is layers. So you can, let me try to get a little bit better. There's alternating layers of light and dark, and they form these lines. So if I set this down here, I've got a light layer with a dark layer, and then a lighter layer, and then some more dark layers. Plus, it's also shiny. It's got lots of uniform, spread out crystals. That lets me know it's metamorphic. So metamorphic rocks tend to, why it's not focusing anymore, tend to have layers and be fairly shiny. And if I take, actually these two, shale is a sedimentary rock. It's not very, it's just kind of a plain Jane rock. It's formed by clay particles that get cemented together or compacted together. But if I take that shale and I put it under heat and pressure, I form one that's got a similar color called slate. They actually made chalkboards, like the really old school chalkboards with slate. And you can see how it's kind of got these different layers. So it's got these ledges, which you can actually use to break this into nice flat sheets. And then you can draw on it with chalk. So that's why they used it for chalkboards when they couldn't use shale because it hadn't gone under heat and pressure to form all those nice layers. Okay. And then I think that's good enough at this point. So if I come back here,
I think you're muted.
can you hear me now?
Yes.
So, the last thing I wanted to just briefly point out and show is another document that you've already seen for the minerals. I don't think you've seen it for the rocks unless you went ahead a little bit. It was the ID table. Right. So I showed us some of these rocks here today. We had Gabbro, which didn't quite look the same like this. It didn't have quite as much white, but they were dark colored. And it just, this sheet here kind of goes over the different types of stuff that I just showed you. Like if you cool slowly, you're going to have these big crystals, ones that you can see. If you cool fast, you're going to have very tiny crystals that you might not even see at all. So they're going to be much smaller. And then we had our obsidian and pumice. I showed you pretty much all of those today, other than a couple. Then the layers in the metamorphic rocks are called foliations. That's the really fancy name for a layer. So I showed you some that had layers like slate, and I showed you some that didn't have layers like the marble, I believe. Yep, marble right here. Okay. And then the sedimentary rocks were up above. We had sandstone, which it literally just says if your grains, your sediments are about this size, they're still visible, it's going to be sandstone. If they're smaller, like shale, like I couldn't see the particles in shale. Where is shale at? Right here. No grains, but may feel gritty. So that's shale. If it's, could be siltstone too, but it depends on some of these other ones. So we're going to be using some of these for worksheets, I believe, possibly. I just wanted to briefly point it out at this point, just so you knew it existed. It's still on Google Classroom under the mineral assignment, but I'll repost it with any rock assignment coming up later on. So otherwise, that took a little longer than I was expecting, but I did show you a bunch of rocks. So, are there any other questions at this point?
How long does this process take?
How long? Okay, yeah. It could be relatively quickly to do some of these things. Like breaking a rock down can happen quickly, but in general, it's going to take, at the very least, a couple thousand years to form some of these sedimentary rocks, because you got to have enough of them to actually get enough pressure to cement them together or fuse them together. Or granite cooling is going to take a couple thousand years, but if you form obsidian or the pumice, the one that was floating, that happens from a volcanic eruption that's pretty explosive or happens on the surface, and it can cool fairly quickly. Like if in the mid-ocean ridges, when the magma comes up there, it forms these pillow basalts or pillow obsidians, these little round balls of rock essentially. And since it's literally touching the ocean water, it cools off in probably a couple hours. So
how did that make the pumice get to school?
It was in a cabinet.
Oh, it was bought or something. It
Yeah.
wasn't just in the backyard.
No.
Oh, okay.
The only ones that were in my backyard were some chunks of limestone and the sandstone that I had.
Oh, okay.
I could probably go out and find some granite chunks. Like, that's worth pointing out. Like when you see rocks in the field around here, because there's a lot of rocks in fields, those were eroded here. They were moved here by glaciers. So when you go out, and I've done it with my kids to get rocks for landscaping or whatever, you go wander around a field and you pick up a rock around here, it probably didn't form here. It was dropped off when the glaciers came down this far and melted and started moving back and receding. So we kind of are on the end of a glaciation area, and we just end up with a lot of random rock chunks that are laying around. So
Okay.
otherwise, okay. If we don't have any other questions, thanks for stopping in today. I hope it was a little bit more interesting than a YouTube video, more worth your time. I think I showed the rocks better than I did the minerals because I had my phone going and you could see them a little bit better than me doing this. But otherwise, that's what I have for you for today, is just the notes. So if you're done with that and you've done the quiz that we had come up on Monday, other than the project, which you're doing 2 days this week, that's what you're doing for science. So
Thank you.
yep. Yes, I can get you a drink, he said. Okay, I will stop the recording and I'll post that. So if anyone asks you like, oh crap, I forgot to watch or join the Zoom video, I'll let them know that it's gonna be on Classroom. So
Okay.
bye, Lena. Okay.
Why don't you